Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Alexis Claude Clairaut's 1750 treatise, The Théorie de la Figure de la Terre, Tiré des Principes de l'Hydrostatique, stands as a monumental achievement in the history of physical science. It represents far more than a simple geometric inquiry into the planet's shape. It is a profound synthesis of Newtonian gravitational theory, advanced calculus, and fluid mechanics, which collectively resolved one of the most contentious scientific debates of the early 18th century. The work's brilliance lies in its methodological innovation, its theoretical generality, and its enduring influence on the development of mathematical physics, particularly potential theory and celestial mechanics. Clairaut's essay elevated the discussion from one of empirical measurement and geometric conjecture to a rigorous analytical problem, demonstrating with irrefutable logic how the Earth's form is an observable consequence of the fundamental laws of nature. To appreciate its full significance requires an exploration of the intellectual landscape it transformed, a deep analysis of its internal mathematical architecture, and a tracing of its powerful legacy through subsequent generations of scientific thought. The genesis of Clairaut's work is found in a direct and unresolved tension inherited from the titans of the preceding century. Isaac Newton, in his Principia Mathematica, had posited that a rotating, self-gravitating fluid body should assume the shape of an oblate spheroid, flattened at the poles and bulging at the equator. He arrived at this conclusion through an ingenious thought experiment involving two communicating canals of water, one running from the pole to the centre of the Earth and the other from the equator to the centre. By balancing the gravitational attraction and the opposing centrifugal force on the equatorial canal, he deduced a specific value for the Earth's ellipticity. Parallel reasoning from Christian Huygens concerning centrifugal action supported this general conclusion. This theoretical model, however, faced a significant empirical challenge from within France itself. The meticulous geodetic surveys conducted by the Cassini family, Jacques and his son César-François, over several decades, seemed to indicate the exact opposite. The measurements of meridian arcs suggested that a degree of latitude was longer in the south of France than in the north, implying a prolate spheroid, a body elongated along its rotational axis like a lemon. This discrepancy created a deep intellectual schism, pitting the followers of Newton's universal gravitation against the empirical authority of the French Royal Academy of Sciences. The very validity of the Newtonian system seemed to hang in the balance, as its prediction for the planet's shape appeared contradicted by the most precise measurements available. This was the complex and high-stakes environment into which Clairaut introduced his definitive theoretical intervention. The Théorie de la Figure de la Terre itself is a masterwork of analytical mechanics, marking a decisive move away from the geometric style of Newton toward the powerful new language of differential calculus. Clairaut's central and most crucial assumption was that the Earth could be modelled as a fluid body in hydrostatic equilibrium. This principle asserts that at any point within the fluid, the pressure is uniform in all directions, meaning the net force on any small element of the fluid is zero. Consequently, the surface of this fluid body must be an equipotential surface. This means that the sum of the gravitational potential and the potential associated with the centrifugal force is constant everywhere on the surface. Any particle on this surface could be moved to any other point without any work being done against the combined forces of gravity and rotation. This conceptual framework was immensely powerful because it translated a complex physical problem into a purely mathematical one, finding the shape of a surface upon which a specific potential function remains constant. To solve this, Clairaut deployed a mathematical technique of breathtaking novelty and power. He was among the first to systematically use what we now recognize as potential theory. He expressed the gravitational attraction of the spheroid at an arbitrary point as the gradient of a scalar potential function. This function, v, depended on the mass distribution throughout the body. The components of the gravitational force in any direction were then simply the partial derivatives of this function with respect to the spatial coordinates. This was a profound abstraction that bypassed the need to perform complex vector summations of forces from every particle of the Earth, a computationally impossible task. Instead, the entire problem was encapsulated in the properties of a single scalar field. Clairaut then developed this potential function as an infinite series expansion, using what are effectively the zonal spherical harmonics, specifically the Legendre polynomials, although their full formalization would come later, with Adrien-Marie Legendre and Pierre-Simon Laplace. This series allowed him to approximate the potential of a slightly deformed sphere to any desired degree of accuracy, providing a flexible and powerful tool for analyzing bodies It deviated from perfect sphericity. The intellectual climax of the treatise is the formulation now universally known as Clairaut's theorem. This elegant and powerful relationship connects the physical and geometric properties of the rotating body in a stunningly simple formula. In its full spoken form, the theorem states that for a rotating spheroid in hydrostatic equilibrium, the sum of the gravitational acceleration at any point on the surface and 1/2 of the component of centrifugal acceleration perpendicular to the rotational axis, when divided by the acceleration at the pole, is approximately equal to 1 plus a term that is the product of a constant and the square of the sine of the latitude. More famously, it yields a direct connection between measurable quantities. It relates the flattening of the Earth, denoted F, which is the ratio of the difference between the equatorial and polar radii to the equatorial radius, to the variation of surface gravity. Specifically, it can be expressed in the form that the sum of the flattening and the ratio of the centrifugal force to gravity at the equator is related to the ratio of the gravitational variation from pole to equator. A simplified and highly practical version of the theorem establishes a direct link between the flattening F and quantities related to the variation of gravity with latitude. This was a revelation. It meant that one could determine the geometric shape of the planet by making precise measurements of gravity at different latitudes using a pendulum clock. The rate at which gravity changes as one moves from the equator to the poles is directly tied to how squashed the planet. Furthermore, Clairaut derived a general second-order non-linear ordinary differential equation that the shape of the rotating body must satisfy. This equation, Clairaut's equation, was remarkable for its generality. It did not require a uniform density, a simplifying assumption Newton had been forced to make. Clairaut's analysis showed that for any plausible density distribution that increases towards the centre, the resulting equilibrium shape must be an oblate spheroid. He thus proved that the Cassini's empirical results were incompatible not just with Newton's specific model, but with any gravitationally consistent model of a rotating fluid Earth. This provided the definitive theoretical death knell for the prolate spheroid hypothesis. The immediate impact of Clairaut's work was profound, as it provided the indispensable theoretical framework for interpreting the results of two of the most ambitious scientific expeditions of the era. The French Academy, in an effort to resolve the shape controversy through direct measurement, had dispatched two teams, one to the equatorial region of Peru, led by Charles-Marie de la Condamine, Louis Godin, and Pierre Bauger, and another to the Arctic Circle in Lapland, led by Pierre-Louis Maupertuis, with Clairaut himself participating in the latter. These expeditions undertook the grueling task of measuring the length of a degree of meridian arc. Clairaut's return from Lapland in 1737, with data showing a degree of latitude was indeed longer in the north than in France, provided the first strong evidence for an oblate Earth. The later, though much more arduous, results from the Peruvian expedition confirmed it. Clairaut's 1750 treatise was the theoretical culmination of this immense effort. It demonstrated how these arc measurements, along with gravimetric data, could be used within his mathematical framework to calculate the Earth's flattening. The theory and the observations converged beautifully, cementing the victory of the Newtonian worldview and turning the figure of the Earth into a precise parameter of a universally applicable physical. The later use and evolution of Clairaut's ideas demonstrate their foundational importance. His work on potential theory became the starting point for the next generation of mathematical physicists. Pierre-Simon Laplace, in his monumental Traité de mécanique céleste, took Clairaut's concepts and generalized them into a comprehensive theory of potentials. Laplace's famous equation, which states the sum of the second partial derivatives of the potential function with respect to the Cartesian coordinates is zero in empty space, is a direct and powerful extension of Clairaut's method. Laplace, along with Legendre, formalized the theory of spherical harmonics, providing a complete set of orthogonal functions for solving potential problems on a sphere, a tool Clairaut had pioneered in a more rudimentary form. The entire edifice of celestial mechanics erected by Laplace, which described the motions of the planets and their moons with unprecedented accuracy, rests on the analytical foundation that Clairaut had laid in his study of the Earth. Clairaut's work received further validation and refinement in the 19th century. The Irish mathematician and physicist George Stokes, in 1849, revisited the problem and proved a remarkable extension of Clairaut's theorem. Stokes demonstrated that the external gravitational field, and thus the relationship expressed in Clairaut's theorem, depends only on the total mass, the rotation rate, and the surface shape of the body. It is completely independent of the specific internal density distribution, as long as the surface is one of hydrostatic equilibrium. This generalization, known as Stokes' theorem in geodesy, made Clairaut's result even more powerful and of greater practical use, as it removed any uncertainty related to the Earth's unknown interior composition. This led directly to the modern concept of the geoid, defined as the true equipotential surface of the Earth's gravity field that best fits mean sea level. The entire science of modern geodesy, which uses satellite measurements and gravimetry to map the geoid with extraordinary precision, the direct intellectual and methodological descendant of the problem first solved by Claire. The reception of the theory was overwhelmingly positive, as it settled a long and acrimonious debate with a display of undeniable mathematical power. It cemented Clairaut's reputation as one of Europe's leading mathematicians, alongside figures like Leonhard Euler and Jean Laurent de Lambert, the latter of whom was a fierce intellectual rival who worked on similar problems. The principal critique, or rather the primary area for future refinement, lay in the foundational assumption of hydrostatic equilibrium. The Earth is a complex body with a solid, elastic mantle and crust, whose rheological properties are far more complex than those of a simple fluid. However, over geological timescales, the mantle behaves as a highly viscous fluid, as the assumption of hydrostatic equilibrium remains an exceptionally accurate first approximation. Subsequent work in geophysics has focused on understanding the departures from this ideal state, but Clairaut's model remains the essential baseline against which all more complex models are compared. It provides the reference ellipsoid, the idealized mathematical surface that serves as the foundation for all modern mapping and coordinate systems. It is perhaps the ultimate testament to his genius that a model derived from pen, paper, and the principles of fluid mechanics in 1750 continues to underpin the satellite-based global positioning systems of the 21st century. In conclusion, Alexis Clairaut's theory de la figure de la Terre is a seminal work that fundamentally reshaped the landscape of the physical sciences. It drew its motivating problem directly from the unresolved legacy of Newton and the empirical contradictions posed by the Cassini surveys. Its core contribution was the introduction of a new and profoundly powerful analytical paradigm centered on potential theory and the principle of hydrostatic equilibrium, articulated through the new language of calculus. The work's central tenets, Clairaut's theorem and its governing differential equation, provided a framework of beautiful generality, proving the necessity of an oblate Earth and connecting its geometry to observable gravitational phenomena. Its immediate application vindicated the grueling expeditions to Peru and Lapland, while its long-term influence provided the essential groundwork for Laplace's celestial mechanics and the entire modern science of geodesy. Clairaut's essay stands as a landmark, not merely for solving the problem of the Earth's shape, but for demonstrating how abstract mathematical reasoning could unlock the deepest secrets of the physical world, setting a standard for rigor and elegance that would define mathematical physics for centuries to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.